Okay, so what we're gonna do, I'm just gonna work through some of these problems so you get an idea of where your downfalls could potentially happen.
Like the problems on the assignment?
No, this is just like a sample problem. But it's a similar type of thing to what you do on the assignment.
All right.
Okay? So, here's the situation. Here's the planet, and the satellite is orbiting 122 kilometers above
Bluetooth.
the surface. Okay?
Which question is this like? Are you
I don't know.
All of them.
They're kind of all. Because there's only a certain number of equations you can use.
Yes.
So here's the deal. So we want to calculate the velocity, the period, then we want to calculate the centripetal acceleration and g at that altitude. Okay? So here's the first thing that you have to do.
Meters.
This is in kilometers, which you're going to have to change into
Meters.
meters. So divide by 1,000 and tell me that that thing is orbiting 0.122 meters above the surface of the Earth. Let's multiply by 1,000. So you got 122,000 meters. Now, is that what you're going to use as the radius?
No, you gotta add
No.
the radius of Earth.
Because listen to me, we're treating everything as a point mass, okay? So anytime, like there's a problem on here with something orbiting the moon, Lunar Command Module orbiting the moon, you have to add in the radius. Now, but here's the difference. If I had said, this thing is orbiting at an orbital radius of 6.5 times 10 to the 7th meters. If I tell you it's the orbital radius, that is already measured from the center of the Earth, or the moon, or whatever it is. The only time you have to add in the radius is if you are specifically told this is the distance above the Earth. If you're just told that's the radius, you can use it straight up, okay? You don't have to add that value in. So, when you do this, you got 122,000. So this is why you want to store these numbers in the memory of your calculator. So somebody take 122,000 and add in the radius of the Earth.
649.
Now, when you get this number, do not round it. Okay? You keep all of these digits. You round when you get to the end, but you keep all of these digits. So what do you get?
6493300.
So 6.49
6.4933. Yeah.
times 10 to the 6th meters. Okay?
Yeah.
Boom, there we go.
Yep.
That's going to be your radius. So that's what we're doing is we are treating the Earth as a point mass. We're treating that satellite as a point mass, and this is how it's going to play out mathematically. Okay. Now that we have that number, if that starts wrong, everything is going to go wrong. Okay? That's why you want to make sure that you have that right and don't round it. So now let's talk about the velocity. This is a fairly straightforward one. You're going to use V equals the square root of big G M over R. Now, what you'll see a lot is that, and if you really want to get fancy, what you'll see in almost all of these equations is that as long as you're orbiting the Earth, you'll always see that big G is multiplied by the mass of the Earth. So if you really want to save some time, you could get fancy and store the product of big G times the mass of the Earth as a separate value. You'd have to be pretty hardcore, pretty lazy. No, I don't want to punch in G times M. I want to have a separate, it's up to you. Now, do not touch a calculator. Step away from the calculator right now. Step away from the calculator, okay? Step away.
Step away.
Louis?
Step away.
from the calculator. I want to just look at order of magnitude on this thing, okay? So, I got 6.67 times 10 to the negative 11th times the mass of the Earth, 5.979
10 to the negative 23, or 23.
times 10 to the 24th
That's close.
divided by 6.4933 times 10 to the 6th meters. Okay? Now, I got 10 to the negative 11 times 10 to the 24th, which gives me 10 to the
13.
13th. So I got 10 to the 13th divided by 10 to the 6th, which gives me
2 point some.
10 to the
7.
7th, and I'm taking the square root of
No,
that,
subtract them. Yeah.
which as a ballpark gets me 10 to the 3rd. Okay? Now, listen to me, listen to me, listen to me, listen to me, listen to me. When you calculate an orbital velocity of anything in a near-Earth orbit around the Earth, that velocity is going to be 10 to the 3rd. Okay? If you get 10 to the 4th, train wreck. If you get 10 to the 2nd, train wreck. Okay? Every orbital velocity you're going to calculate from near-Earth orbit is going to be something times 10 to the 3rd. Okay? It's not a weird number to remember. It isn't like 3.91. Oh, it's 10 to the 3rd. So if you calculate a velocity and you get 10 to the 6th, bad. Okay? I can guarantee you probably forgot to take the square root of something. Okay? So all of your velocities, listen to me, are going to be 10 to the 3rd. No exceptions. It isn't like, oh, Bergkamp's tricking me. He just wants to see if I'll fall for it. I'm not. Okay? You did something wrong. And so help me. If anybody writes something 10 to the 8th faster than the speed of light, I will completely flip out. Okay? I'm just telling you right now. I always get an answer faster than the speed of light. Every year I pray to the physics gods that I don't, but every year they never listen. Okay? So, every velocity is going to be 10 to the 3rd. So now, run the numbers. Now, step up to the plate on your calculator.
Yep.
And trust me, make sure that you can do these things on your calculators. Some people like to divide and conquer, like they'll do all the computations, then they'll take the square root of it. Some people would put it in brackets and do it all at once. I don't care.
Got it.
So, what
get
did you
84?
get?
7.8 times 10 to the 4th. Okay,
7.
10 to the 3rd.
What?
Louis?
I got
Seven.
I don't like
7.912.
I got 7.836.
I did it.
Yeah, 836. That's what I got.
I guess it's
What?
8.7 if you round.
Yeah, Vitor is.
What do you mean, bro?
Victor, you were
Hey, are
saying-
you in radio mode?
That doesn't matter.
I am, though.
Well, it won't matter.
Why did I get 7?
7,911.
What'd you get? 7,000 what?
911.
That's what I got, too.
I got 836. What values do you guys
Well,
have
it's,
for math?
yeah, it's what you have for mass and radius.
5.979.
I'm wrong. I'm wrong.
Okay, then you're wrong.
How?
I'm wrong.
Why?
I did it wrong.
Why?
How did you do it wrong? It's literally like
Well, because
just
I
put
said
GM. Just put GM.
That's what I did. I don't know
What do
why.
you have
What'd you get
for
for
mass
GM?
of the Earth?
Oh, never mind. I know.
Victor, it's the bottom one. The
Yeah.
radius is different.
Yeah,
That's
yeah,
what we did
yeah.
wrong.
Nah, we're good. We're good.
We use the radius.
I forgot.
Yeah, but you have to use
Yeah, you have
that.
to add it in.
Yeah.
We just
Okay, so what did you get?
all
Hold on,
right.
let me.
7.837
So
times
7.83
7 times 10 to the 3rd. That's what we got. That's what
meters per second. Okay?
That's real fast.
That's fast.
That's fast.
Okay? That's fast. Again, that's roughly about 5 miles per second. Yeah, you're hauling the mail. Okay? So that's why I said this would be the old. So if I could go outside and throw this baseball, and we didn't have an atmosphere, but if I could go outside and throw this baseball at that speed, it would be in orbit around the Earth. Because what's going to happen is that the Earth is going to curve out as that exact distance, and it kind of makes sense. So if I take this baseball, just give that a little bit of a toss, right? It travels a certain distance before it hits the ground. If I throw it faster, then it travels an even greater distance before it hits the ground. And the faster I throw it, the further it goes before it hits the ground. And if I could throw it fast enough to match the curvature of the Earth, the baseball would be in orbit.
I wish I was.
Louis,
Does it matter which way you throw it?
there's going to be so many
What?
other issues. You actually want to throw it like on an easterly direction because that's the way the Earth is spinning.
Okay, because like, I feel like is there like a universal way to like have your satellite rotate?
No, you can have circumpolar.
Oh, okay.
Yeah, but we'll talk about why you always want to launch from the equator. But we'll get to that later. Okay. All right. Now let's calculate the period. So the one for the period you're gonna start with that 4 pi squared r cubed equals big G mass of the earth times t squared. This is the one that I'm gonna give you on the test, okay? That's exactly how it's gonna be written, because that's the Swiss Army knife version. You can do so many things with it. So, if you solve for t, you got 4 pi squared r cubed over big G mass of the earth, square root of that. Now, at this point, there's a couple of things you could do. It's a personal preference thing. Some people like to pull out that square root of 4 pi squared and write it as 2 pi times r cubed over big G mass of the earth, okay? If you want to leave the 4 pi squared underneath there, that's completely up to you. Now, step away from the calculators, step away from the calculators. We're going to do order of magnitude again. So my radius is 10 to the 6th, but that's going to get,
Cube.
so that gets me
18.
10 to the 18th. Down below I got 10 to the negative 11th times 10 to the,
24.
which gives me 10 to the,
13.
so 10 to the 18th divided by the 10 to the 13th gives me 10 to the square root of that. Again, is going to give me about 10 to the 3rd. So here's the beauty. Orbital periods in seconds are also 10 to the 3rd. You don't even have to remember two different values. Orbital velocities, orbital periods in seconds are going to be 10 to the 3rd. Okay? Not 10 to the 2nd, not 10 to the 4th, 10 to the 3rd. So if you do this calculation and you get like 0.05 seconds, you have done something horribly wrong. Okay? And I've seen that answer. Okay? How long does it take for the lunar command module to orbit the moon? 0.05 seconds. Really? Okay? Or I get really big answers like longer than the universe itself has existed. So, 10 to the 3rd. That's all you have to remember. 10 to the 3rd for your velocity, 10 to the 3rd for the orbital periods. Okay? But that's in seconds. Okay? You have to keep that in mind. That's in seconds. Now, let's do the math.
Bluetooth.
Let me get rid of all of this. So we'll put in the actual numbers.
Can't even wrap my head around
That is crazy.
That is like if us three got put on there by ourselves, we can not get Bluetooth.
Like, you this water bottle, bro. Where did this come from?
There's no chance, no
So we got
chance.
4 pi
We would
squared.
die before we got computers.
What was the radius? 4.6 point,
6.4933 times 10 to the 6.
How'd you find the number?
and that's going to get cubed divided by big G mass of the earth. Now, let me give you all a hint, and I've seen some of your work. Solve these equations for the variables first before you put in the numbers. It is so much easier to solve and just put M as opposed to rewriting the mass of the earth 3 times. Okay? And that's how real science is done. The last thing that you do is you put in numbers. So trust me on this one. Save yourself a lot of time. Solve the equations first. You're not in Algebra 1. You're running with the big dogs. Solve the equations first.
The big dogs.
The big dog.
So, what did you get as an answer?
5.206.
I thought you said don't touch your calculator.
Yeah, I didn't.
Now, what'd you get? 5 point what?
206.
I wanna see
Do you
what I
want 3 significant digits on these?
That's
as well?
fine.
Times 10 to the third.
Seconds.
But what do you want? Like on a assignment?
3.
Okay.
Now, so we can have, notice this is 10 to the 3rd. How cool is this? Now, divide that by 60, so we know how many minutes that is.
8.6.
Oh no, that's
No. That don't get it in scientific.
86.8.
86.8
Oh,
minutes.
yeah.
So about an hour and a half. Okay? So what that means is this satellite is going to make a loop around the Earth every hour and a half. Okay? So if you're in this particular ship, you're going to see the sunrise every hour and a half. You're going to see the sunset every hour and a half. Okay?
terribly wrong.
So if you like sunrises and sunsets, it's kind of a cool place to be.
What did I do wrong?
Okay,
What's big D again?
got those.
No.
The struggle with these is not the calculations, it is the
6.67
concepts.
times
The struggle
10 to the
is
negative
basically, can you run your calculator? Can you not make simple
Pop, you need a
mistakes and
better
forget the square roots and
I do.
things like that? Okay, now here's the most important part. I want to calculate the centripetal acceleration.
Wait, can you
Hold
go
on.
back? Can you go back a little
Take
bit,
chill
please?
cell for a second.
Okay, so I have an absurdly large number, and I
Is it
plugged
in
it in
radio
exactly like that.
No.
Are you in a
Okay,
radio?
let me
was
ask you
times
this.
10 to the
When
27.
did you do it all in one step?
What do you mean?
Did you like get this number separately and then divide by G and then divide by the mass of the Earth?
No, I did 6.44 or 6.49 the radius deal, and then I cubed it,
Yeah.
right? So and then I just divided by GM
Now, did you put GM?
in parentheses. No, I didn't.
So what happened is that you divided by G and then you multiplied by M. You have to put those in brackets if you're going to do it that way.
I'm still losing.
Yeah, that's
Hold on.
a wee bit better. It's a wee bit
A
better.
lot better.
Yeah, it's a bit better.
That's the other thing that happens. You have to pay attention to your order of operation. Or the other thing that happens is that you're so excited about getting done inside of that, and then you forget to take the square root. Okay? And then you put down 10 to the 6th, and then I have to snarkily circle that and go, really? Really? Think about that.
It's a bit
Okay.
long.
Pop, did you get it?
No, he doesn't look like he's got it.
He's making that. He's that.
Okay, we'll move on. We'll get back. We'll circle back.
I'm getting 10 to the 22nd on the top. That's the call.
Which maybe, and that's after you multiply by 4 pi squared?
Yeah.
That's not, might be reasonable. Because 10 to the 6 is, and that's leaving out cubing the 6.4933.
No, that's after cubing. So you cube that, and
Then you
then
multiply by 4 pi squared.
And I'm getting 10 to the 22nd,
Let me see.
1.08.
No, that's right. Yeah, that's right.
Yeah.
That's right?
And then
Yeah,
you
we
divi-
just
And then
estimated
you
that to be 10
divide
to the
by
18.
CGM.
Yeah, so the. Hold on.
He's
I
gonna
don't
get
know.
it. Watch. He's
Is
gonna be
it,
like,
is
oh.
it? My bad. This is it right here. Is M the 6.37?
I don't know what you have stored where.
I don't
Yes,
know
M
either.
is 5.97
Oh,
times.
there we go. Okay.
You need a better
Dude, get a
calculator. This dude got A,
calculator,
B,
bro.
and C, and that's
Hey,
it.
hey, that's kind I use back off.
Oh, but it's good. Like I'm saying, but
It's
Five,
good
two,
for
five,
it's good for
values
2
and
plus
stuff?
2,
Got it.
5205.
not
You
storage
got it?
of values.
Okay.
Got it, okay.
Okay.
I do need. I'm
Show
I'm
me
gonna
show
need
me
to
a
get new
parabola on
calculator.
that.
Okay, anyway, all right, so back to our story.
I'm
Back to our story.
parabola.
We gotta focus.
Exactly.
We got tracks to make.
Get yourself a parabola.
So now I want to calculate the centripetal acceleration. So why do you know that this thing is even undergoing centripetal acceleration?
it's moving in a circle.
It's moving in a circular path, right? So there's a couple ways you can do centripetal acceleration. One option is that you can use v squared over r. You know the velocity, you know the radius. That's an option. You could use 4 pi squared r over t squared. Now you know the period. Okay? Which one do you want to use?
V squared R.
That's what I would use. Okay? So somebody take that radius, or that velocity,
Squared it.
square it, and then divide that by, and don't use the radius of the Earth because you're not orbiting at the Earth. You're orbiting 120 kilometers above the Earth. Okay? So somebody take v squared, that velocity, divide it by the radius at that point. Let me know what you get. Now, do you think your answer is going to be bigger or smaller than 9.8 meters per second squared?
Smaller
Okay.
than 9.8 meters per second.
Yeah. What'd you get?
Small.
It's gonna be the same.
I don't feel like I did it right.
What'd you get?
It's the same because it's
9.45.
What'd you get?
9.45.
About 9.45?
Yeah.
Yep, 9.4.
Yeah,
Cool with that?
9.46, yeah.
Yes.
Really.
Okay? Now, just bank that number for now. Just bank it. Bank it. Now I want to calculate little g, which I always thought would be, if I ever became a rapper, that would be my stage
Oh,
name.
little G.
Give it up for little g.
Little G.
Now, So I want to calculate little g. Now, here's the conceptual thing that I want you to see. Imagine that here's the Earth, and we're going to build a ladder that's 120 kilometers tall. Okay? So imagine we're on top of this ladder. It's 120 kilometers tall.
But your brother's shaking the ball.
And I'm going to drop a rock. Okay? Will it begin to fall towards the Earth?
Yes.
Yeah.
Yes, we're still very much inside the gravitational field of the Earth, right? So, here's what I want you to look at.
Oh.
If you plug in the radius of the Earth, where we are right now, if you take big G times the mass of the Earth times the radius of the Earth, where we're at right now, what do you think you're going to get for little g? You're going to get 9.8 meters per second squared. That's our gravitational acceleration. But now, look what's happened to this value of r relative to where we are at the surface. Now, you're on top of this ladder that's 120 kilometers tall, okay? Which would be about 65 miles, okay? Now, you're going to be divided by a bigger number. So what's going to happen to that value of little g?
It's smaller.
It's going to become smaller, okay? So we're not, even on top of that ladder, we're not in zero g, okay? We're still very much within the gravitational field of the Earth. And we have to be, because if we're not in the gravitational field of the Earth, bad things are going to happen. So now I want you to calculate little g doing this way. Big G, mass of the Earth, that's why I said so many times, big G is multiplied by the mass of the Earth, okay? So, and again, you got to divide that by that radius of 6.4933 times 10 to the 6th meters squared. What did you get?
6.1
No, you didn't.
4 times 10 to the.
No, you didn't.
Wrong.
I got 9.45.
You got 9.45.
Yeah.
You should.
See, I didn't even
I
do
didn't-
it.
What
I
did
didn't
you
swear.
get?
Vitor, what did
I
you
didn't
do?
swear.
This is what I'm telling you. You have the potential to get more answers that make no sense at all in this unit than any other unit you were going to study. Now, you got 9.45.
Yeah.
Coincidence?
No.
No.
Absolutely
I
not.
think not.
Okay? Because here's the deal. What's creating the centripetal force?
Gravity.
Gravity. Here's a simple idea. We're going to go, oh, the centripetal force equals the gravitational force. Oh, that's mass times your centripetal acceleration, which is mass times your
Gravitation.
Gravitation.
masses cancel out. Guess what?
They equal.
They equal each other. Okay? So if ever I ask you to calculate the centripetal acceleration of the satellite, by default, you are also calculating the gravitational acceleration at that point. Okay? Because they have to be the same thing. Louis.
So, if you were in the center of the Earth, would you just float?
Yes. If you could be in the absolute center.
You'd just be floating.
Because you'd be pulled in all directions.
If
Of course, you'd be on fire, but small details.
if you stand on like a ladder high enough and like you drop something and does the rotation of the Earth like affect where it
Oh, the
lands?
Coriolis effect? Yes.
Yeah.
Oh, there's going to be so many things that are going to get you like that. When it hits the atmosphere, it's going to start to burn up anyway. Anyway,
So whenever we were like doing the other ones, whenever we're dropping stuff and we just use 9.8, technically where you are on the Earth, wouldn't that like affect like what the acceleration is, like if
Yes.
you're higher elevation or something?
exactly.
Or
So, like,
physics,
if you
so
go
we
to-
ignore
if
that.
if you go to Denver,
Uh-huh.
technically, you weigh less in Denver than you do here.
So that's why they do the
Oh.
jumping there.
What?
The ski jumping.
No, no, no.
Wouldn't you,
That's
like-
just because it's
Oh,
cold.
that, yeah, that.
Because it has
And it
snow.
has snow.
It
It's
has
gonna be-
snow.
But wouldn't
It's
that,
gonna be like
wouldn't it make a
9.79 per
But
meters per
it's,
second.
but they're all, but everybody's jumping under those conditions.
Yeah.
Now, you go to the top of Mount Everest, that actually becomes a little bit more pronounced because of the fact that you are. So this is what I want you to see. Little g on Earth is not technically a constant. We always use 9.8, but technically it changes depending upon your elevation. Big G is the universal constant. That's 6.67 times 10 to the negative 11. So no matter where you are, big G isn't going to change. Little g doesn't. Does change because that's dependent upon how far you are from the center. Okay, that was the most complicated of all the problems that we have to work with. Whew, that was a task. Okay, but it was also some of the most important things that you gotta do.
Donkin on Mount Everest.
I'll be Duncan.
Donkin.
I'll be doing between the legs.
Now,
and Everest.
this next calculation is very relevant in terms of how we figure out what's going on in our solar system. So, let's say that we've got a planet that we
What
found,
is happening?
and we know that it has a moon, and we've observed the moon, and
Got a little robot.
here's the planet, here's the moon.
It's a little slow.
And we know that it takes 20.5 hours for the moon to go around. What?
TV's not doing anything.
You're alive.
It's being.
Whoa!
Whoa!
It's been in
Ooh,
today.
you got a little buddy helping you out there.
There's a little behind.
You should just
Time
write it
delay.
out and then
Just a
like
little bit.
talk through it. That'd be cool.
Yeah. Stop!
Cut it out. Cut it out.
Why would you do this, Vitor?
Cut it out.
Oh, don't even. Don't even.
Cut it out.
Okay.
No problem. This is what I think about this.
No.
What did I do?
You're
Go.
doing it about water. What are you gonna do?
Okay.
I'm gonna put the paper airplane.
So this is how
Shake
this
that around.
actually plays out in terms of if we want to find
Bless you.
the mass
Bless you.
of a planet.
I wonder if this calculator does it.
We figure out what happens with a
I wonder
moon
if
that's
this
orbiting.
calculator does it.
So
Yes.
the only way you can do this is go that
Yes, you
4
can.
pi squared r cubed equaling big G mass
Battery.
times t squared. Okay?
What is it, just that?
Now, here's what you're going to do wrong. You mark my words. What units does that t have to be in?
Second.
Seconds. And here's the reason why. That big G is in newtons, meters squared over kilograms squared.
Uh-huh.
And those newtons are kilograms meters per.
Second squared.
Here's what you're gonna do wrong. You mark my words. You're gonna see those 20.5 hours, and that's what you're gonna put in there for T. You mark my words, that's what's gonna happen,
Yeah.
okay? Mark my words. And you all sit there and go, Mr. Burkamp, we won't do that. Don't be so evil. Why?
We won't do that.
Okay? And here's what's gonna happen. You're gonna get either an exceedingly small mass, or you're gonna get a mass bigger than the sun. And it would be like a black hole. Okay? And then, or the worst answers, you get answers that are like bigger than the observable universe. Okay? In terms of mass. So, what you want to do is solve for this m. Okay? And that m is whatever is at the center of this. So if I solve this for m,
4 pi squared r cubed over
GM.
GT
That
squared.
needs a charcoal.
You're solving.
so I'm solving for mass,
Realistically,
right?
put on the
So I'm going to divide by big G,
where do you think we could get to?
T
You could get
squared.
to, like,
okay? I don't have to do anything weird with it, okay? That's all I got. So I'm going to have
To get to the electricity.
okay,
4
we
pi
already know
squared.
Do we already know it? I don't think we
The
know.
basis.
Now,
Okay.
notice on
How do
this
you get
one,
electricity?
Plug it in.
I didn't tell you that that was the distance above the
With the
planet.
umbrellas in?
When I gave you this value, that's the number, okay? You don't have to add in the radius of the planet, because you couldn't add in the radius of the planet anyway, because you don't know what the radius of the planet is, okay? So when I give you a number like this, just use it straight up. That's it, all you have to do. Then you got G, and then T squared, 20.5 hours. 1 hour is,
60 minutes.
or 3,600 seconds if you want to do it all in one step. So here's what you're going to do. You mark my words. Even if you remember to change that into seconds, that's kind of cool. You're going to forget to square it. Okay?
Yep.
Promise you, you're going to forget to square it.
Computer
And then
almost
you're going to
forgot.
be off by about 1,000. Okay? So, run the numbers.
Run it
Let's
up.
run them.
Run them.
This is kind of fun. I don't know why.
Now, this falls under those, when I was a kid, speeches. My high school physics teacher wouldn't let us use calculators on the test.
No way.
True story.
Did you have to do this same
You had the
stuff?
book. You each
No
have like a
shot.
big book that you're like flipping through.
Yeah.
Let me
Is
give
this
you
the
all
kind
the
of stuff you had
answers.
to do too? Did you have to do?
Well,
stuff
but
like-
he would just make us basically get to this point without actually crunching the numbers.
Oh, okay.
Let's see.
Sometimes he
bad.
would, but that was pretty rare.
Yeah. Like in your head? I mean, on.
Well,
Yeah, in your head.
Or you just work it out by hand.
Jeez, that would be a lot of work.
That
It was
would
horrible.
that would take
Yeah.
so long.
I know.
And that was the thing. It was just like, come on. Are you testing our knowledge of physics, or are you testing our ability to crunch insanely large numbers?
Exactly.
Both.
Exactly.
I
Exactly.
forgot.
And
Mr. Burkett.
So, what'd somebody get? Who's gonna throw it out first?
hold up.
You throw that again before.
I'll throw it. I'll throw my number out first.
Let's hear it, Paul.
5.42 times
Hold on.
10 to the 21st.
What'd you get, Jackson?
5.42 times 10 to the 21st.
5.42 times 10 to the 21st?
Yeah.
What's Big G? What's Big G?
6.67.
I did
times
a
10 to the
bad.
negative
I did a
11.
bad.
What'd you do, Louis?
I did the thing.
You forgot to swear it.
No, Mister. We could never do that, Mr. Burkamp.
And right
You
away,
lie.
what did you do?
lie.
You lie.
10 to the 21st? No.
Oh no.
Oh, I had it.
Are we talking about the what? Wait, what mass
We're
are we trying to
talking-
find?
We're
Yep,
trying to
I got
find
it.
the mass of the planet.
I got it.
Our planet?
No,
No.
the mass of the
Of
planet
the
in
planet?
this problem.
Does it happen to be bigger than Earth?
No.
It's 5.415.
I got 8.119
Eight
times
point
10 to
one
the
one nine
31st.
times
That's 10 to the what?
31st.
Okay,
How'd you get that, bro?
okay, that's 5 times bigger than the mass of the sun.
Oh my
That is
god.
not right.
Lewis.
Ah, I screwed up.
And you all laughed and said,
You lie.
You lie.
You say you
Uh-huh.
love do that. Look at me on my small boy
Alright,
calculator
bro.
got the right answer.
uh-huh.
Get it away from my
Yeah.
face.
It's
I
five.
got,
Yeah,
I
it's
may only
5.
have A, B, C, and D.
Hey, that's what I got.
Okay,
We
is everybody
I have
cool?
5.418.
Yeah, except for Louis.
This is why I said you
I
have
have
to get good
5.1158.
at using your calculator.
Do we
Well,
square it at
158,
any
yeah.
point?
Yeah.
Yeah.
Or square root it?
No.
No,
You probably put the you put the G squared as well. You squared G.
Wait, where does it say you square G?
You
don't.
squared
You
you squared G.
That wouldn't do
Oh.
anything. That wouldn't make it
Yeah,
bigger.
yeah, I did.
That wouldn't
Yeah, I
make it
did.
bigger.
Because I multiplied
He squared
G
G
and
as
then
well.
squared
You're supposed to multiply and only
Yeah, but
square
how
the
would that
time.
make it bigger? That would make it
because
smaller.
you're dividing by 10 to the negative 22nd as opposed to dividing by 10 to the negative 11th.
But would that make it bigger or smaller?
Yes, you're dividing by a much smaller number.
Come on, bro.
Because
It's negative. It's negative.
If you
Negative
square
Oh, yeah,
G,
it's
then
negative.
you're dividing by 10 to the negative 22nd.
Oh. I
As
thought it was
opposed to
positive.
dividing by 10 to the
I thought it was
negative 11.
positive 22nd, so that was my fault.
Are we good?
You got it.
Okay,
Good.
It's just one thing, dude.
fantastic.
Fan.
Okay, on this last one,
I see. Why is it so small?
all right. So on this last one, I don't want to go through all the math because I got to get through some other stuff, but I just want to kind of lay out the main idea.
It's so loud.
Still zooming.
Don't go it.
Is it really?
It
I
was.
just
It
stopped.
was.
It's so weird. It has never done that. Okay. Well, let's go even weirder. Okay. So here's the radius of the moon. And then
It's got
We
a
have a
3-second delay.
we land on the moon
have a game, bro.
and we drop an object and we measure that acceleration and it's 1.22 meters per second squared. So this is what we did basically when we landed on the moon. We had the radius of the moon
I
and
hope we have.
we measured the centrifugal acceleration. So help me God.
Oh my days.
Beat 'em up.
Louis, for the sake of my own,
I'm not gonna do anything.
Take the principles off.
Rip it
Here,
up.
here, ready?
Unfold it.
Oh.
Whoa, are these cheats? It's got codes down.
okay. So
Causes.
you're gonna go little
Telegram.
g equals big G mass of the planet over r squared. So this is literally what we did to find the mass of the moon. They landed, they took a pendulum, they measured the value of gravitational acceleration from the pendulum. We knew the radius of the moon, we knew big G, we solved for that. Okay, so there's two ways that you can find the mass of a planet or a moon. You can either figure out the information about something that's orbiting it, or you land on it and you know the gravitational acceleration and the radius of the moon. Those are your two options. So basically, you're going to come in here and you're going to find the mass of the moon. You got girth squared over big G equals your value for the mass. Okay? So, we're going to save some time. Y'all know how to do that. You've got your calculators out. Life's good. Now, so here's the deal. But here's this is going to be relevant to one of the questions that you have on your assignment. I said, what distance would we need to go so that a 1 kilogram mass weighs 1 newton? Okay? So, if you have a 1 kilogram mass and you're standing on the planet, what would a 1 kilogram mass weigh? Good job, Jackson.
1.22 kilogram. Wait,
No.
Newtons.
Newtons.
My bad.
All right? Now, how'd you get that, Jackson? What did you do?
1 times the accelerator, gravitational accelerator.
Yeah, you said Fg equals mg. You took 1 kilogram times 1.22 meters per second squared, and you got 1.22 newtons, right? Now, so basically, I want this thing to only weigh 1 newton. So what do I want little g to be?
1.
1 meter per second squared. So there's a couple of ways you can approach this. One is that you go back to this equation, and instead of 1.22, you set that equal to 1 meter per second squared.
Yep.
Now you know big G, you know the mass of the moon at this point. Solve for R. What does your value for R have to be bigger than?
The radius.
Yeah, it has to be bigger than the radius of the moon. Okay? Because you're going to be at some distance up here so that when you drop something, and instead of accelerating at 1.22 meters per second squared, it accelerates at 1 meter per second squared. Okay? So that's one option. The other thing that you could do, this is a personal preference, is that you could go old school.
Yeah. Old.
Okay? Now, this is actually a deeper truth if you go with this route. You want a 1 kilogram mass to weigh 1 newton. So you can come in and go, oh, that's going to be 1 newton. Boom, there you go. That's what you want the force between that 1 kilogram mass and the moon to equal. 1.
Yes.
You know what big G is. You know one of those is 1 kilogram. You know the other one is the mass of the moon itself. And you solve for R. Okay? So this is actually, it's more math, but it actually shows a deeper understanding. Because now you're going, oh, cool. That weight is 1 newton. So when you talk about when something weighs, you're talking about that gravitational attraction between that object and the moon, the planet, whatever that you're on. Okay? Got it. Now, before I forget, unfortunately, hopefully you guys can't make it because you're still playing. But the telescope night is going to be Tuesday night at 7 o'clock. Okay? That's because it's supposed to get cloudy on Wednesday. Thursday it's supposed to rain. So that's basically the only shot that we have. So going to be Tuesday night, 7 o'clock. We'll talk more about it, but if you want to kind of put that on your calendar, we're going to meet out here on the south end of the high school.
Oh,
So
cool.
supposedly we
you
got
guys
this
going
really new, phenomenal telescope. I haven't even looked at it yet, so I don't know what the images are going to be, but from how it's hyped, it should be pretty cool. So,
Oh, do we not get to look through it? It's a digital one?
no, you'll be able to look through it.
Oh, okay.
Yeah, there'll be eyepieces, and we can have different filters and.
Cool.
Yes. Okay, but it's cool because you can like once you get it set up, you tell it to sign, find like Saturn, and it'll automatically rotate around
Dang.
and find Saturn.
How does it know where Saturn is?
you plug in your GPS coordinates, and then where it is, it basically
Oh,
has
you
a
can
star
like plug
map
in the
story.
date too, huh?
Yeah, so you
Oh,
gotta
okay.
plug in everything, where you are, the exact time, and then it basically does that calibration and goes, okay, we're here, Saturn should be here, we're gonna
That's
find it
crazy.
at that point.
That's
like-
crazy.
How much does it
How accurate?
Yeah.
How accurate is it?
From how, what they hype it, it's like spot on, like boom,
Oh, wow.
there you go.
Watch it just like
So,
zoom in on the
now,
wrong planet.
there's like, you have it like, I gotta download the app on my phone, and it's the whole deal.
How much was it? You know,
But I didn't realize.
I wanna say it's like $1,200.
that's
That's not
eight.
bad.
Yeah.
I'm gonna buy myself a telescope.
It's not bad.
Okay.
I don't have it back in.
Anyway, so
$200.
stop
I
that.
don't have it back in.
Let's go to the back. Okay. Hey, all right, so this is spandex. And so if you look at the history of gravity, Kepler came along, he developed his three laws, he really didn't try to explain what happened. Newton comes along and says F equals big G M1 M2 over D squared, okay? But again, it worked, but the mechanism really, no one really understood that. Einstein comes along and he says, hey, you know, we can view space and time as a fabric. And so this is what this is representing, is space and time. Okay?
I thought it was flat.
I thought it was a table too.
Okay? So, but you can actually study all of Newton's laws in one simple idea. So if I just take a single marble and roll it across, notice the path is straight. Okay? First law of inertia, right? Objects travel in a straight path until one outside force acts upon them. So if we go this way, okay, and it will roll, and what's the only reason it slows down?
Friction.
It's friction. Now, I take another mass and I put it in there. Okay? So that would be like the sun at the center of our solar system. This is creating a distortion in space and time. Now when I roll it,
Oh.
notice that it travels in, instead of in a straight line, it travels in a curved path. Okay? So Einstein says the reason objects fall when I let go of something, it's just following a curved path of space and time. So right now, you all are curving space and time. It's like, oh, that's cool. Okay, everybody does it. Get over it. Don't feel special. Okay? But here's the cool thing. Everybody focuses on that little object going around like this. But you can actually observe Newton's third law and the second law in this as well. Because if you notice when it goes past it, that bigger mass wobbles just a little bit. Okay? Now, that's Newton's third law. For every action, there is a reaction. So as this is going around, that's creating a little bit of a wobble. So everybody says, oh, the Earth is pulling on the satellite. It is. But guess what? What's the satellite doing?
Pulling back.
On the Earth.
Pulling back on the Earth. Oh, the Earth keeps the moon in orbit. True, it does. But guess what? What's the moon doing?
Pulling back.
Yeah, it's pulling back on the Earth, which is why we have tides. Okay? Now, so that's a simple system. So let's say that we want to model
The soul.
the Earth and the moon. Okay? So let's say we want to go to the moon. So first off, this is actually horribly complicated because the Earth is moving and the moon is moving as well. So the analogy of trying to get something to actually land on the moon is standing on one end of a football field, having an orange at the other end of the football field. And you have a .22 rifle, and you have to shoot the orange that's 100 yards away and nick the orange peel. Okay, so that's kind of an analogous difficulty in trying to get something actually to land and orbit the moon. So here's the short version of what happens. So we launch, we orbit the Earth a couple times, make sure everything's cool. Then we fire the engines and we begin to go towards the moon. Now, notice that, and this is a nice way of modeling this. Notice that the Earth has a deeper gravitational well than the moon does. So if we orbit this and we fire the engines and we're not going fast enough, guess what's going to happen?
Go back to crash and burn.
We're going to crash and burn. We're just going to fall back into it. So but what's going to happen, but as you get further from that gravitational well, the gravitational field becomes weaker and weaker and weaker. So that's where calculus plays a function in this. Because as you travel, that pull from the Earth is getting weaker and weaker and weaker. But what's happening to the gravitational pull towards the moon? That's getting stronger and stronger and stronger. So what happens is that, and this is some of the calculations you're going to do, it's known as Lagrange points. It was named after a French mathematician that came up with this concept. So if I put the marble here, it rolls towards the moon. If I put the marble here, it rolls back towards the Earth. So what does that mean?
There's a sweet spot.
There's a sweet spot. It's like the crest of the gravitational well. So if I can find that one point right there, it's like a tug of war. So that means the gravitational pull towards the moon is equal to the gravitational pull back towards the Earth. So if you could, and this is this whole idea of Lagrange points, there's actually like 6. We're just going to do 2. What that means is if you could park a spaceship right here, you wouldn't have to fire the engines at all. It would stay locked in that position in an equal tug of war between the moon and the Earth. So this is Lagrange point 1. Lagrange point 2 is out here. The other ones are, those get even weirder. We're just going to worry about Lagrange point 1 and Lagrange point 2.
What's Lagrange?
So if you go past that, though, then you begin to accelerate towards the moon. If you're on this side of it, you're going to accelerate back towards the Earth. Okay? Now, where things get really weird, somebody hand me another 200 gram mass. Or when you have like a binary star system. Okay? So if you have a binary star system, then you get
What?
some really weird things going on, because now you have like a double curvature of
That's cool.
space and time. Oh yeah, you can just play with this for hours. Okay?
What if you have triple star?
No, see, actually, if mine were my brother would have to. Yeah, it is. So my brother would have to like shoot me, because if we have a blood pact, if either one of us were spandex, we have to shoot the other one. So I can't.
Why?
It's just a thing with my brother. Or drive a
Spandex is
minivan
weird,
or
bro.
rollerblade. Those are the 3 things.
When did those start?
Spandex. Yeah. Diapers too, but that, yeah. Okay.
That's later.
You're gonna do that. That's just, sorry, I'm gonna have to shoot you. Okay. So, yeah,
Will you follow through?
huh?
Will you follow through?
I don't know.
drives me
Maybe,
neat.
it depends on the day. Okay, so one of the things you also talk about, and we'll talk more about this when we get into energy, something known as escape velocity. So escape velocity is basically how fast you have to go to get out of a gravitational well. So if I, and here's the classic example. So if I roll this and throw this up, notice it comes back down. If I throw it faster, it goes farther, but it still comes back down. So if I could throw it fast enough, it would go out of that gravitational well. So if we want something to go towards the moon, we have to reach the escape velocity and surpass that, or what's going to happen is that it's just going to fall back down. So if you want to escape our solar system, you have to get out of the escape velocity of the sun. But your escape velocity is a function of distance. Escape velocity for Mercury to get out of the sun is much bigger than the escape velocity is for Mars. Because with Mars, you're already starting on the shallow part of the gravitational well. So you don't have to go as fast. So if we want to launch something outside of our solar system, it's easier to do that from Mars than it is from Earth, because of the fact that you're farther away from the bottom of that gravitational well. Okay, let's go back.
Can you show us like the second Grange point?
It's just going to be Well,
How does that even? Yeah, how does that
like
even work?
with the Earth too, though?
yes,
Is that how the stuff works?
yes, well, yeah, that's not, the thing. And that's going to be question number 7, okay? So I'm gonna show you 2 ways you can do this. One that's horribly complicated, one that's a little simpler.
Yeah,
It depends
I like
upon
simple.
how much of a pure mathematician that you wanna be. But here's the basic idea.
I mean, it's like,
Here's the Earth, here's the Moon. Here's our Lunar Command Module, okay? And we're going towards the Moon. So basically what we want to find is the point in the middle where this thing feels an equal pull between the Lunar Command Module and the Earth, and the Lunar Command Module and the Moon. Okay, so it's like a tug of war. At that point, you're at the top of that gravitational well between these 2 objects. So, we can sit here and go, okay, to calculate this force, that's going to be big G times the mass of the Lunar Command Module times the mass of the Earth times some distance that we don't know. So that's just going to be x. But that's going to get x squared because it's Newton's law, right? Okay? So this first calculation gets us the force between the Lunar Command Module and the Earth. Seriously.
You lost your paper.
oh, I'm sorry.
And
That door.
You know why I don't teach freshmen?
Freshman activities, Pop.
Now,
who put it back together, Louis?
that has to equal the mass of the Lunar Command Module multiplied by what?
Gravity.
Nope,
The mass.
mass of the Moon, right?
The moon mass.
Now, the tricky part comes with the distance. The entire distance between these points, and I've given you this, is 3.844 times 10 to the 8th meters. That's the entire distance between the Earth and the Moon. So here's the point. If this distance is x, what's left over?
3.844 10 to the 8
Minus
X.
x.
Bingo. 3.844
Yeah.
times 10 to the 8th meters minus x. But what's going to happen?
Squared.
That's going to get
Squared.
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 Now at this point, this looks horribly complicated. You're going to
Yeah, I don't like this.
suck. But, what's going to happen to your big G?
They're gonna cancel out.
That's going to cancel out.
Lunar mass.
What's going to happen to the mass of the Lunar Command Module?
It cancel out.
It cancels out.
Yeah.
So right away, this becomes simpler. Okay?
Not much simpler.
Well, I'm just going to save some. Now, I'm going to cross multiply because I hate fractions. So I'm going to take the mass of the Earth
Times that
times
abomination.
3.844 times 10 to the 8th
Squared.
minus x squared. And that's going to equal the mass of the Moon
X.
times x squared. Now,
So far.
I want to simplify this. So I want to divide both sides by the mass of the Moon. Okay? So you've got the mass of the Moon. It's 7.35 times 10 to the 22nd kilograms. So I want to make sure everybody has this number. So I'm going to take the mass of the Earth and divide that by the mass of the Moon. Let me know what you get.
Which one's the mass of the Earth?
Bro,
M.
you need it.
Bro, you need help.
Which one is it?
You need help.
It's a big M.
Is it the
8.135.
What's the mass of the moon? That's a better question.
8 point, no, don't give it as a scientific notation.
81.
Point
35.
Is this the mass?
81.35. We're gonna keep more digits than we need,
Okay.
okay? So this has no units at this point. This is just a ratio. So what this tells me is the mass of the Earth is 81.35 times greater than the mass of the Moon, okay? That's that number. Now, that's gonna equal 3.844 times 10 to the 8th minus x, quantity squared equaling x squared, right? Okay? Cool with this. Now, here's the deal. I want to take this, so here's option number one. Okay? Option number one. You expand this binomial.
Please no.
Okay? Just like if you have 5 minus x, quantity squared, go old school. What do you get if you expand 5 minus x, quantity squared?
X squared minus 2 times that thing x.
X squared,
Yep.
x squared
And then
minus
and then that
10x
thing
plus
squared.
25.
Got
Right?
it.
So, you,
It's 5
Plus
minus
25.
10x plus 25.
right? 5 squared. So imagine doing that with these numbers.
Yeah.
You can do it, but it's just going to get god awful big numbers. Not only do you have to do that, then you have to distribute the 81.35 over that.
Yeah.
And you can do this, okay? But then you eventually want to use the quadratic formula, negative b plus or minus b squared all over 4, right? And then you got to move x squared over there, and then you're going to have 0 on one side, and you're going to have a huge number in front of your x squared, and then a number in front of your x, and then another number that you're going to plug into the quadratic formula. Okay, and it'll be the most complicated quadratic formula solution you ever find. And if you're hardcore and you want to do that, you can. That's an option. I didn't say you had to do it, I'm just saying it's an option. Now,
Dumb option.
here's your other option. What if we take the square root of both sides?
Good idea.
Ooh.
Okay? What if we do that? What's the square root of x squared?
X.
Okay, that's kind of cool. Now, somebody get me the square root of 81.35.
It's 9.02.
9.02.
Oh my god.
Now, technically, that's going to be plus or minus, right? Technically, that's going to be plus or minus. And then times 3.844 times 10 to the 8th minus x. So here's how you can solve this without going through the quadratic formula from hell, okay? But this is how you solve it twice. Situation number one, you take 9.02, and you take 9.02 and you distribute it this. You move the x over to one side, it becomes an algebra 1 problem. Okay? And you get everything on one side, you get your x's on the other, boom, there you go. Then to get the second root, you take the negative 9.02 and distribute that. Repeat the process. You get all your x's on one side, you get the numeric values on the other, boom, solve for x. Okay? So this is how you're still going to get your 2 roots, just without going through the monstrosity of dealing with the quadratic formula. Okay?
Wow.
Got that. Now, what you should see, here's your 2 Lagrange points. One Lagrange point is going to put you between the Earth and the Moon. So one Lagrange point is going to be less than the distance to the Moon. Your other Lagrange point is going to put you somewhere on the other side of the Moon. Okay? So this is where the Webb telescope is actually parked, is in one of the Lagrange points relative to the Sun and the Earth. Okay? So it's quite a ways, it's way, way out there. But we do that for a couple of reasons. It stabilizes our orbit, and we're also in the shadow of the Earth. Okay? So we'll talk more about that later. All right, so let me give you some hints on some of your answers. Okay? Let me give you some hints.
Hints as in, ooh, is that the answer key question mark?
Give me your answer.
What did you ask?
I said, how is that?
So if this goes bad, everything's going to go
What do you
bad.
mean?
So your answer to number 1 should be something times 10 to the 3rd.
Yeah.
Okay?
So should number 2.
Oh, it's where they're both.
Your answer to number 2 is 10 to the 7th. Okay?
Wait, what was number 1?
10 to the 3rd.
10 to the 3rd. Number 2 is 10 to the 7th. Both of your answers on number 7 on your Lagrange points should be something times 10 to the 8th. Okay? Make sure that you answer, there's a question that you need to answer in addition to finding the Lagrange points. On number 8, you're finding the mass of, I think, Saturn.
Yeah.
That should be something times 10 to the 26th. Okay? When you get to question number 9, we're talking about a geosynchronous satellite. Okay, so what happens on a geosynchronous satellite is that as the Earth spins on its axis, that satellite stays above that same point all the time. So that's what you have to have your GPS satellites. Because that way you're triangulating your phone off of these fixed points. So on a geosynchronous satellite, the orbital period is 24 hours. So what happens as the Earth spins, that satellite stays at that same point above the Earth all the time. That's what allows you to have a fixed reference point. And so what happens is that we have this parking lot of geosynchronous satellites that you're always bouncing your signal off of, and that's what allows you to figure out, wow, you know, I've got 3 miles to go before I turn, because you're bouncing that signal off of these parking lots of geosynchronous satellites. So, when you get to this question, okay, so the reason that I'm going to give you this distance from Kansas City to Wichita is because that's going to give you some reference in terms of, wow, how far is this thing, okay? So the other thing that you want to do when you get to 9C, I've given you the speed of light, 3.00 times 10 to the 8th meters per second. So what I'm asking is that how long will it take for a signal to travel from your phone to that GPS satellite? So your phone is continuously communicating with these. So you've got your phone, there's a geosynchronous satellite. What you're going to calculate, and your phone is on the surface of the Earth, okay? Right? That's why on this one, I'm asking you, how high above the surface of the Earth? So what's going to happen, you're going to solve for R. That R is going to be from the center of the Earth to that satellite, okay? So when you find your initial value of R, that's from the center of the Earth out to here. We need to the surface because that's what our calculations are going to be based upon. Okay, you're not at the center of the Earth; you're on the surface of the Earth. That's why you need to subtract out the radius of the Earth. So when you're figuring that time, use the distance from the surface of the Earth to the satellite, not from the center of the Earth to that satellite. Okay, so just kind of that visual. Anyway. So we'll talk a lot more about these problems tomorrow. And like I said, if you want to hand it in tomorrow, you can. Or you can hand it in the day of the test on Friday.
Wait, is today Wednesday?
Yes.
Yes.
Oh, I was so confused.
Zito, you kind of stay in here and work on this
Right now?
until we have practice. We have like 40 minutes.
Oh, yeah.
Oh, I'd be.
If you want some perspective, here's the length of the answer keys.
Oh my.
So how long did you say? Like an hour and a half? For
Hour
you,
and a half
for
is
you.
what?
It sounds worse than what it actually is. The hardest, the solving the equations isn't that tough. That one for the Lagrange points is tough, but I pretty much got you started on that.
Yeah. Can you?
So,
what are like the main? What are the equations that we derive all of this from? Aren't there
the
like?
main idea is that your centrifugal force is equal to your gravitational force.
Yeah.
MV squared over R equals
And so
big
if
F.
I-
Yeah.
The gravitational force
And
is
that-
just F equals
MG.
Yeah.
over R squared.
Over R squared.
Over
Yeah.
Irish
So
square?
it's over
Irish?
R squared.
Yeah.
You got an Irish laugh.
Wait, what? Is it time, Big
Friday
G?
for a debate tournament?
Are you going to be here in the morning? Yeah, stop that.